Section 14.7, extreme values and saddle points. In other words, we like to find the absolute maximum minimum or relative maximum minimum and ultimately do word problems called optimization problems. If you recall from single variable functions, if you were trying to find the extreme values of a single variable function, you were supposed to find the critical values. How did you find the critical values? By setting the derivative equal to 0, or find the values of the derivative, values of x, which made the derivative undefined. So those were the critical values, and once you find those critical values, then you can look for maximum or minimum or point of inflections. If you recall, we have covered all that in single variable function. So the methods we applied there were either first derivative test or second derivative test. And if you remember, the second derivative test was like if you have a single variable function, which happens to be twice differentiable on some open interval I, containing the value x equals 0. If f prime of c was equal to 0, and f double prime was less than 0, at that point x equals c, then we said f has a local max at x equals c. Local, sometimes it's known as relative. Okay, so local means what? Relative to the nearby values close to x equals c. On the other hand, if you set the derivative equal to 0 and the second derivative was positive, then f had a local mean, or as I said, a relative mean. Where? At x equals c. If f prime was 0 and f double prime was 0, then the test failed. So now we have, come up with some other strategy. Perhaps we have to graph the function and see if we have a relative maximum mean. In other words, the function may or may not have a local maximum mean. So obviously the test is inclusive. So we have to come up with plan B, either by graphing the function or by other means, because obviously the test did not give us a solid information. So in function of several variables, specifically z is equal to fxy, so function of two variables, we say this guy has a relative or local maximum at a comma b, at point a comma b, if f of ab is greater than or equal to for every ordered pair for near ab. In other words, if you have a disk with the center a comma b, any ordered pair you select, the value of the function at a comma b has to be greater than any nearby ordered pairs close to ab. Okay, so this is a disk. On the other hand, if that you're trying to establish the fact that the function has a relative minimum at some point, like let's say a comma b, then you got to prove that f of ab is less than or equal to f of x, y at ab, provided xy is near ab. In other words, you got to find a disk with center at ab, so every other ordered pair in that disk near the point has to be less than or equal to whatever the value of the function is at nearby ordered pairs. So that's a formal definition of relative maximum and minimum value of function of two variables. Before we get into this, let's make sure we know how to find the critical values. Critical points, also known as stationary points, we say a comma b is a critical value such that either the partial derivatives of f with respect to y or x is equal to 0, or one of these partials is undefined, just like single variable case. So either we have to set these guys equal to 0 and look for a critical value, or one of these partials had to be for some order pair for x and y has to be undefined. So in other words, we can go back and what? Convert these formal definitions for relative max or mean to absolute max or mean. How? In order to say the function has absolute maximum, then f of ab has to be greater than or equal to f of xy, not for any order pair near AB, but for all order pairs in R2, which means on the xy plane. So if this inequality holds for any, not the ones nearby AB, but any order pair on xy plane, then f of AB is the absolute maximum. Otherwise, if it is less than or equal to for all, incidentally, this notation in the land of mathematics means for all. For every order pair in R2, then f of AB is called absolute what? Minimum value. So let's see what is the proper test we have to apply. Remember in the first, what was it, semester calculus, we applied second derivative test. We could have applied first derivative test. We have almost similar test to that second derivative test. It's called d-test or second derivative test. And it goes something like this. Suppose the second partial derivatives of f of x, y are continuous on a disk. Okay, you can no longer have an interval, so you have to have a disk now because you're dealing with what? Order pairs. With AB and what? With the center at AB and the partials being equal to 0 at that point. So D is defined, you know, as fxx evaluated at AB times fyy evaluated at AB minus the mixed partial evaluated at AB quantity squared. So this is the definition of what we call the D function. Do you see it? So it's fxx evaluated at AB times fyy evaluated at AB minus the mixed partial quantity squared, this guy squared. So now we have different scenarios. If this function d is greater than 0 and fxx is also greater than 0, we say the function has a relative minimum at a comma b. If d is negative, but fxx is also negative, then, excuse me, this is supposed to read positive, sorry. If this, d is positive, just like before, correct? But fxx is negative, then we say the function has relative maximum at what? At AB, okay? If d is negative, regardless of what the sign of fxx is, we say the function has neither maximum nor minimum. So that would be a point which we call a saddle point. Sometimes people call this minimax. In other words, if you look at the saddle, something like this, if you look at it from the top is minimum. If you look at this saddle from the bottom is maximum. So it's neither max or what? Mean, so it's saddle point. If d comes up to 0, you know, this function which I defined inside the box is 0, then the test fails. So we have to try something else. What do you mean by try something else? Well, graph it. Graph the surface and see by inspection if you can tell what relative maximum or minimum value of the function is. The reason they chose letter D because D stands for determinant. So this is a 2x2 determinant whose components are partial second order partials. So the main diagonal elements are fxx, fyy. The off main diagonal elements are the partial what? mixed partials. But remember, Mr. Clairaut proved that the mixed partials are equal. So therefore, if you just go, as one of my students told me the other day, if you go the loop, so this would be fxx times fyy minus fxy squared, because the partial mixed partials are equal. So that's why the letter D. So now let's do an example quickly to see if we can find what? All the relative maximum, minimum, or saddle points for the following functions. Here's my function, xy minus 2x minus 2y minus x squared minus y squared. So how would I find, all the possible relative max or mean? There is no guarantee there is one, but if there is, or there are relative maximum, minimum points, I'd like to find them. Well, one of the criteria is the function has to be continuous, just like, single variable function. So looks like this is a polynomial kind, so everything is a-okay, so we can go ahead and look for the relative max and mean. So what's the step one? Immediately take the partials, set them equal to 0. Why? So I can find the critical values. So this would be my critical value. You see it. Now, that's the only critical value you got, so test drive it. That means what? Evaluate the D function at critical value, -2, 2, and turns out you get like 3, which is positive. I really don't care about the number, I just care about the sign of D, evaluated at the critical value. fxx is -2, which is less than 0. So D was positive, fxx negative, according to our rule. So fxy has a relative maximum at -2, -2. Or instead of relative, you can also use the word local. So what is that relative maximum equal to? Go back to the original function, replace the x's with -2, y's with -2, you get 12. This, ladies and gentlemen, is relative maximum value of this function. In other words, for any order pair near -2 and -2, this is as high as the value of the function gets. On the other hand, you may have more than one critical values. Then you have to test drive them all. So let's say this is your function. You took the partials and set them equal to 0, and lo and behold, the system of equation, not necessarily linear, gave you 4 critical values. So what do? You list them all on a table, organize them. So you got 0, 0, 0, 4, -2, 2, and 2, 2. Check the sign of D, check the sign of fxx. Notice for 0, 0, D is positive, fxx negative. For 0, 4, D is positive, fxx is positive. For the remaining cases, D is negative, so who cares what f of xx is? So for these two values, I'm getting what? A saddle point. However, for the first two order pairs, when D is positive, fxx is negative, I have local max at 0, 0, and I have local mean at 0, 4. So you make a table, list your critical values, find out what the sign of D and fxx is, and based on this agreement or the rule right here, determine whether you have maximum, minimum, saddle point, or if the D comes up equal to 0, then the test fails. Do you see it? The other idea is about finding the absolute. That means what? The highest value of the point in the entire what? Graph of the surface. Absolute max and absolute minimum. Once again, let's go back to the what? Single variable functions and remind ourselves, in order to find absolute max and mean, the function had to be continuous on a closed interval. In other words, you have to give me a limitation. Otherwise, I can't go find absolute maximum minimum if you tell me the sky is the limit. So you got to put some sort of restriction on the domain. So therefore, I can find the absolute maximum or minimum. In other words, you got to give me a closed interval. So when that's the case, we do not apply any tests, which we didn't in the case of the single variable function. Notice all we did in previous classes. Let's say you're trying to find the absolute maximum minimum for x squared on a closed interval between -2 and 2. Closed interval means x is greater than or equal to -2, but less than or equal to 1, correct? It's closed. So find the critical value by setting the derivative equal to 0, which that gives you x equals 0. Then these are called endpoints. Okay, those are called endpoints. Then test drive the function at endpoints, meaning evaluate the function at the endpoints. These are the endpoints. And then compare the values and choose the highest as your absolute maximum, choose the lowest as your absolute minimum. It's really a remedial step. In other words, it doesn't take the sophistication of calculus classes, because all you have to do, find the critical value, list it, make a note of the endpoints, list them. Now evaluate the function, which happens to be x squared, at the critical value, at the endpoints, get the value of the function. Choose the highest of these values as your absolute maximum and the lowest as your absolute minimum, and then box your answer because you are so done with this problem, correct? So there it is. So absolute maximum happens right here. I could have told you what the absolute max is by just graphing x squared. And absolute minimum happens to be at 0, 0. And our table agrees with that conclusion. However, the extreme value theorem in for function of two variables goes if f of xy is continuous function on a closed and bounded. First of all, it has to be closed region. So the region has to be closed. And it has to be bounded. That means it also has to include the boundaries. Okay, boundaries. So you have to have a closed region. Instead of closed interval, you're supposed to have a closed region on on the x and y plane, which is closed and bounded in R2. R2 means xy plane. Okay. Then f has an absolute maximum minimum value at some point like A, B, or C, D in the region D. Keep in mind critical points from setting the partials equal to 0. They should be in the interior of the region. In other words, your critical values have to lie in the interior of your closed region, closed and bounded region. If they are outside of the region, they are not considered to be critical values. They have to lie in the interior of the closed region, which they will give you what the region is in any given problem. So now let's do a quick example. These are time consuming, so bear with me. Suppose you have a function 4x plus 6y minus x squared minus y squared, and the region, the set D is this. All order pairs such that x goes between 0 and 4 and y goes between 0 and 5. In other words, you are restricted with this rectangle. Do you see it? So x goes from 0 to 4, y goes from 0 to 5. So that means you have a closed, and bounded region. How do I know it's bounded? Well, notice you have equal signs, correct? So in other words, the boundaries are what? Included. So what's the question? The question is find absolute maximum minimum values of this. So what do? You take the partial derivatives to find what? Critical point or points. In this case, the only critical points you have is 2 and 3. Immediately check and see if that critical value is in the interior of your region. If it is not, then it's not a critical value. Sometimes the critical value might be one of the corner points. These are called corner points, these guys. Do you see it? Those are called corner points. Corner points. Do you see it? They have to be tested as well. But the critical value has to lie in the interior of the what? Closed and bounded region, which, as I said, they will tell you what that region is. So they put a restriction on the domain of the function. Now my job is what? To find the absolute maximum minimum. And the extreme value theorem guarantees that if the function is continuous on a closed and bounded what? Region, I'm guaranteed to have absolute max or mean. There's no way I'm not going to get any absolute max or mean. I'm going to, right? So what do? Hold on to this, put this in back burner, and check and double check and make sure it is in the interior. So this is fine. Now you got to test drive the boundaries. The boundaries are these 4 sides of a rectangle. So what does that mean, test drive? Well, on L1, as you can tell, I'm on the x-axis, y is equal to 0, x goes from 0 to 4. So x varies, but y is constant. Go back to equation number 1, replace the y's with 0 because you are on the x-axis. When you do, your function becomes a single variable function. Now pretend you are in Cal 1, find the critical value of this single value function. Take the derivative, you get x equals 2. But how did you get 2? You pretend that what? Assumed y is equal to 0. So 2 comma 0 is one of your points which you have to test drive it. Okay? Continue on. Now test drive the what? Second boundary, which is this vertical edge of the rectangle. On L2, guess what? X is equal to 4, but y goes from 0 to 5. So x is 4 regardless of where you are on this edge or side of the rectangle. Go back to equation number 1, the original equation, replace the x's with 4, so you get a what? Single value function in terms of y. Take its derivative, find the critical value, and then you will set it equal to 0, solve for y. Y comes up to 3. How did you get 3? Well, you replace all the x's with 4. So 4 comma 3 is your what? Second order pair you have to test drive. Because sometimes, what? The absolute max either happens in the interior or on the boundaries or on the what? Corner points. You don't know, so you gotta take care of all the possible what? Scenarios. On L3, y is equal to 5, but x goes from 4 to 0. Notice the way I wrote it. X goes from 4 to 0 because this kind of direction is going to matter to us later on when we hit chapter 16. Anyways, so go back to the function, replace the y's with 5. When you do, you get a what? Single value function in terms of x. Find its critical value, you get 2. So therefore, the resulting what? Order pair is 2 comma 5. Finally, check L4. What is going on in L4? X is equal to 0 because you're along the y-axis. Okay, go back to this function, replace these x's with 0. You get what? Single value function in terms of y. Find its critical value by taking its derivative, setting it equal to 0. You get 3. So therefore, the critical point which you get is 0, 3. Now you gotta have a long what? Table, which should include the critical point, provided the critical point is in the interior of your region. All those what? Points which you generated or you came up with on the boundaries of the set, and the corner points, you know, like 0, 0, 4, 0, 4, 5, 0, 5. So as you can tell, you're going to have a long table. But the beauty of it is, it's purely basic math. There's no calculus involved, because once you have this, go back and evaluate the function, you note this guy, at these points, these order pairs which came up with, which consist of the critical values, the points which you got out of the boundaries, and the corner points. And now by inspection, see which one is the highest, which one is the lowest. So it looks like this is the highest. So therefore the function has an absolute maximum at what? 2, 3, which is the critical value. And it has 2 absolute minimum, which happens to be at 0, 0, and it happens at 0, 0, and 4, 0. So it's very easy. There is no complicated formulas involved. All you have to do is what? Find the critical values by setting the partials equal to 0. Then you will have a system of equations, solve for x and y. Test drive the edges, which is the boundaries, because you never know, just like in the case of what? Single variable function. Notice my absolute maximum happened at the endpoint. Instead of endpoint, now in function of several variables, I have boundaries. Do you see it? So you never know if the absolute max or min occurs in what? On the boundaries. You don't know. I don't know. So I have to test drive them. So that's why the table is an extremely long table. So then again, as I said, very simple, purely by inspection. List them all, evaluate the function, pick your highest what as your absolute maximum and the lowest as your what? Absolute minimum. So let's do a quick application problem, which you guys have seen this before, but I'd like to do it in a different way. Question is, find the points on the plane z is equal to 2 minus 1/3 of x plus 2/3 of y that is closest or nearest to the point 0, 1, 1, 1. Remember, we did this problem. How did we do it? Remember, we kind of did it by what? Kind of like find the shortest distance between a point and a plane. Remember, we used the what? Projection. And we found out that what? D is a scalar projection of QP onto the normal vector. And we came up with an answer. So suppose now we do it by the methods we have learned in this section, 14.7. How would you do this? Well, select the general point on the plane, call it XYZ. You're trying to minimize the distance. That's what this says. It says find the points on the plane. So this is my unknown right here. Where would I put my finger on the plane such that the distance between the point on the plane and the point outside of the plane or off the plane, which is given to me as 0, 1, 1, is minimum? In other words, what I'm looking for is absolute minimum distance. In other words, if I use the distance formula, which is what? X minus 0 squared, y minus 1 squared, z minus 1 squared. This distance is to be minimized. So we call this objective function. But then the restriction they gave you was not every point in the space, but only those points which they happen to lie on this plane. So that equation of the plane is called subjective function. So objective function is the function which is going to be optimized. Optimized means the best solution. Best solution in this case is what? To minimize the distance between the point and the plane. But the restriction they give you, like in this case, the restriction is, look, not any point in the space, but only those points which lie on this what? On this plane. And that's called subjective function. So objective function gets to be optimized, subject to a condition on side condition. These are called constraint equation. In this case is what? Is the equation of the plane. Anywho, it's tradition that in multivariable calculus or even single variable calculus, instead of minimizing the distance, we minimize the square of a distance. That way we don't have to deal with what? Radical. The question is, how would you know these two functions will give you the same answer? Well, it turns out, just like single variable functions, they do have same critical values, but not necessarily same extreme values, but the critical values coincides. So usually people don't minimize the distance, they minimize its squared. But once you find the critical value, come back to what? The original distance formula and find what the minimum distance is. So instead of minimizing this, finding the absolute minimum of this function, I'm going to find the absolute minimum of its squared. That way I don't have to deal with the radical. So this is my brand new function right here. So what I'm going to do is what? I'm going to first take that function, correct? Remember not to be confused with what? D. If that's confusing, let's call this F. Okay, because I don't want you to think this is that infamous D test. Anyways, so what I do, because the function has to be what? True variables. Why is that? Because if you remember, my test was based on two variables right here, not three. So what I do, immediately replace what? This z with this expression. So that way my function will be a function of two variables, so I can apply the D test. You see what I'm saying? You can't do with three. Although there is a way to go around it, that comes up in next section when we talk about Lagrange multipliers. That's 14.8. So express the function in terms of what now? Two variables. So replace this z with this equation. You know, the equation of the plane. So that way, now you have a function of what? Two variables. So take its derivative. So that would be like what? Fx. And this would be like Fy. Set them equal to 0. And then you get what? Two equations, two unknowns. And notice the equations, they don't necessarily come up linear. Sometimes they do, but sometimes they don't. So I really have to know how to solve this kind of system of equations. In this case, they are linear. So this is purely algebra kind of a problem. When you kind of clean this up, you get this. But using the elimination method, substitution method, remember in algebra classes, I will end up with this solution right here. X is equal to 5 over 14, y is equal to 2 over 7. Okay, so that is my critical value. Now, if you go back to what? To this function, find the corresponding z value, which comes up to, believe it or not, 29 over 14. So at this point, the claim is the distance will be minimized. Now, but this is not what? This is the answer to the question. Remember, the question was, find the points on the plane that is closest to the point 0, 1, 1. Well, there it is. The point is 5 over 14, comma 2 over 7, comma 29 over 14. But this, it does not tell you what the minimum distance is. Now, go back to this distance formula, replace the x's with 5 over 14, replace the y with 2 over 7, replace the z with 29 over 14, lo and behold, you get 5 square root of 14 over 14, or 5 over square root of 14. What do you know? That's exactly what we had when we did it by what? Projection. Of course they should match, because we're talking about the same problem, but doing it in a different way, correct? So this is basically one of many, many, many applications of what? Of optimization problems. Of course, there are more, and we shall see those in class. Thank you.